Hey everyone, and welcome back. Today we're gonna be diving deep into how websites handle like huge amounts of traffic
Yeah,
without crashing,
right.
you know?
Yeah.
And to do this, we're looking at this paper called Consistent Hashing and Random Trees, Distributed Caching Protocols for Relieving Hotspots on the World Wide Web.
Yeah, it's a mouthful.
Yeah, it's a mouthful. It sounds very technical, but
It's a great paper though.
it is.
Yeah.
It's really interesting, and it reveals some fascinating tricks that are used every day, like all over the internet.
Oh yeah, constantly.
Yeah.
Yeah.
So like picture this.
Okay.
Your favorite website, right?
Uh
It suddenly gets swamped with like millions of visitors
uh,
all wanting to see, the latest whatever.
like a viral video or something like that?
Yeah, viral video is
Right. Or like breaking news or something.
exactly.
Yeah.
So how do they keep things running smoothly?
Right.
That's what we're going to be looking at today.
Yeah, and this was a big problem like way back in the early days of the internet.
Oh, really?
Oh yeah, yeah.
Oh, wow.
And the paper actually talks about some specific examples of this.
Oh, okay.
So like one example was the JPL website.
JPL.
Yeah, the Jet Propulsion Laboratory,
Right.
NASA.
Uh-huh.
So back in 1994, you might remember this, the Shoemaker-Levy 9 comet
Oh, yeah.
actually collided with Jupiter.
Right.
And people were, fascinated by this. They wanted to see the images.
Of course.
And they wanted to, find out all about it. And so the JPL website just got absolutely slammed with traffic.
Yeah.
And it just couldn't handle it.
Wow.
Another example was IBM during the Deep Blue versus Kasparov chess match.
Oh, wow. Yeah.
Yeah, so this was back in '97.
Okay.
When the IBM supercomputer Deep Blue played Garry Kasparov, the world chess champion.
Right.
And again, everyone wanted to see who's going to win.
Yeah, of course. Yeah.
So the IBM website just got hammered.
So it sounds like this hotspot problem.
Yeah.
It wasn't just like a one-time thing.
No,
With
it was a recurring problem, yeah.
And it still is, right?
Oh, absolutely.
Yeah.
I mean, think about it. The
Yeah.
internet's just grown like exponentially since then.
It's crazy.
Now we have social media and things go viral in like, a matter of minutes.
Yeah.
So the potential for hotspots is greater than ever.
That's a good point. Yeah.
Yeah.
So how do we even begin to prevent these
Right.
these digital meltdowns?
Well, so one of the key things is something called caches.
Caches.
Yeah.
Okay.
So think of these as like mini servers
Okay.
that are scattered all across the internet,
Okay.
and they store copies of popular web pages.
Oh, okay.
So, when you request a web page, right, you don't necessarily have to go all the way back to the original server.
Yep.
To get it. You can actually get it from a nearby cache,
Okay.
which speeds things up.
Yeah.
And it reduces the load on the main server.
So it's like instead of everyone trying to like squeeze through one tiny door
Yeah.
to get to that viral cat video,
Yeah, exactly.
we're creating multiple entrances, right?
Exactly.
Yeah.
It distributes the traffic.
Yeah.
Yeah.
I like that.
Yeah.
Okay, so the cache has got it.
Okay.
Sorry.
So how do we...
So before we get to the brilliant solution that this paper came up with,
Okay.
it's kind of important to understand like what people were trying before.
Okay.
So there were two common approaches that they were using.
Okay.
One was called proxy caches,
Okay.
and the other was called harvest cache.
Okay. So what are proxy caches?
So in a proxy cache system, you have like a group of users,
Okay.
and they all share a single cache.
Okay.
So it's pretty simple.
Yeah.
But it's got limitations in terms of scalability.
So if that one cache gets overloaded,
Then everyone's in trouble.
yeah, everyone in that group
Yeah.
is going to suffer.
Yeah. Okay, and what about harvest cache? How's that work?
So harvest cache uses a tree-like hierarchy of caches.
Oh, yeah.
So basically, the requests kind of travel up this tree
Okay.
until they find the web page that they're looking for.
Okay.
It's more scalable than proxy caching,
Okay.
but the root of the tree, like the top level cache,
Yeah.
could still become a bottleneck.
Oh, okay.
Yeah.
So both of those approaches, they kind of had their limitations,
Right.
especially as the internet, continued to grow
Yeah,
at an incredible pace.
Yeah, you need something more robust.
Yeah, yeah.
Yeah.
It seems like we needed a better way to do this.
And that's where our research heroes come in,
Okay.
right? They had these two ingenious ideas.
Okay.
One was called random trees,
Random trees, yeah.
and the other one was called consistent hashing.
consistent hashing. Those
Yeah.
sound kind of cool, actually.
They're cool ideas.
Yeah.
Yeah.
So let's start with the random trees.
Well, okay.
What's so magical about them?
So instead of every web page using like the same fixed tree,
Right.
like in the harvest cache,
Okay.
in this new approach, each web page actually gets its own random tree.
So it's like a whole forest.
It is, yeah.
Yeah.
Constantly changing and adapting to the traffic patterns.
So it's like a dynamic network of caches
It is, yeah.
that are constantly like rerouting the traffic.
Exactly.
Okay, I like that.
Yeah.
That's cool.
Yeah. So you don't get any, one cache that's swamped with requests
Yeah.
for that super popular page.
That makes sense.
Yeah.
But what about like what if servers go offline
Right.
or new ones come online or even just, my internet connection is a little bit flaky.
Right.
How do we make sure that the requests still find?
Right. How do you keep track of all that?
Yeah.
How do you make sure that the request still goes to the right place?
Exactly.
And that's where consistent hashing comes in.
Okay, so consistent hashing is
It's like giving each web page a special map that guides the request to the right cache.
okay.
Even if some of the caches,
Yeah.
disappear or become unavailable.
It's like an address book for the internet.
Yeah, kind of, yeah.
Or-
But it's self-adjusting.
Self-adjusting. Okay,
Yeah.
so it adapts as things change.
And it's
I'm starting to get it, but I still think it sounds a little bit like magic.
well, I mean, it's all about minimizing disruption, right?
Yeah.
So, imagine you have a bunch of boxes
Right.
and you want to distribute balls evenly among them.
Okay.
Right? Consistent hashing is kind of like having a system where even if you add or remove boxes,
Okay.
the balls only need to shift slightly to
Ah.
maintain the balance.
So the balls are like the requests.
Yeah.
And the boxes are the caches.
The caches, exactly.
Okay, I see.
Yeah.
That's pretty cool.
Yeah.
That's a good analogy.
So with traditional hashing,
Yeah.
like if you made any change to the system, you'd have to like remap everything,
Okay.
which would be really inefficient.
Right.
So consistent hashing allows for these smooth transitions.
Okay.
It minimizes the disruption
So this is all happening behind the scenes all the time
all the time. Yeah.
on all the websites that we visit.
Yeah.
That's amazing.
It's pretty amazing. Yeah.
But doesn't adding all these extra steps, like
Right.
the trees and the hashing and the rerouting,
Right.
doesn't it slow things down?
It's a good question. And actually, the paper addresses that.
Okay.
So the extra delay from using multiple caches
Yeah.
is actually pretty minimal.
Okay.
Especially because the data can be transmitted in a kind of a pipelined fashion.
Pipelined, okay.
Yeah, so think of it like a relay race.
Where each runner passes the baton as soon as they get it. You don't have to wait for the previous runner to finish the entire lap.
Gotcha.
Yeah.
Okay, so the data is moving quickly, but
Yeah.
what about storage?
Right.
Like, do we need to have these massive caches
That's another good question.
to store all this stuff?
And again, the paper talks about this.
Okay.
So the thing is, caches only need to store the pages that are requested frequently.
Okay.
And the researchers actually came up with some pretty clever ways to minimize the amount of storage that's needed.
Oh, okay.
Yeah.
That's pretty smart.
Yeah.
Okay, so we've talked about how,
Right.
we have these caches that are distributed all over the place.
Yeah.
But the internet isn't just about computers, right?
Right.
It's a global network
Yeah.
with all sorts of different connection speeds.
Yeah, absolutely.
So how does consistent hashing handle that?
Well, so that's where this concept of ultrametrics comes in.
Ultrametrics, yeah.
Okay.
It's a way of representing the hierarchical structure of the internet.
Okay.
So basically, some connections are faster than others.
Yeah.
Right?
Right.
So you can think of it like a map
Uh-huh.
where the distances represent the connection speeds.
So if I'm connecting to a server that's like across the world,
Right.
it's going to be slower
It's going to be slower.
than if it's,
Right.
in the same city.
Exactly.
Yeah.
Yeah, and the researchers actually adapted their system
Right.
to work efficiently in this real world scenario.
Uh-huh.
So they wanted to make sure that even users with slower connections could still benefit from consistent hashing.
That makes sense.
Yeah.
Wow, this is some pretty impressive stuff.
It is, yeah.
We've covered a lot of ground here.
We have.
We talked about the problem of hotspots.
Yep.
And the limitations of those early solutions,
Right.
like the proxy caches and the harvest
Yeah.
cache. And then we got into these ingenious ideas of random trees
Yeah.
and consistent hashing.
Yeah, powerful combination.
Yeah, very cool.
Yeah, it really is a powerful combination.
Yeah. Yeah.
But it's important to remember that, no system is perfect.
Right.
There are always going to be trade-offs and potential downsides to consider.
That's a great point. And it actually leads me to a question for you, our listener.
Okay.
What if this incredible power of consistent hashing
Right.
could be used for things beyond just web caching?
Ooh.
Could it be applied to other areas where we need to distribute information reliably and efficiently?
That's a fascinating question.
Yeah.
We've seen how it helps to keep websites from buckling under pressure.
Yeah.
But what other problems could it solve?
Yeah.
Could it help with things like video streaming
Uh-huh.
or online gaming or even like handling financial transactions?
Right.
The possibilities seem endless.
Yeah. Yeah.
Yeah.
And what about potential downsides? Are there unforeseen consequences to using consistent hashing on a massive scale?
Mm-hmm.
These are definitely things worth thinking about.
Yeah. Definitely.
And this paper was written back in the late 90s.
Right.
The internet has evolved dramatically since then.
Oh yeah.
We have, social media,
Mm-hmm.
the Internet of Things,
Yeah.
artificial intelligence, like
Yeah.
all this stuff.
All this stuff.
Actually, speaking of how the internet has evolved,
Yeah.
the paper actually mentions something that kind of ties into that.
Oh, okay.
They talk about handling pages that change frequently,
Oh, right.
like, say, a live news feed or a stock ticker, things like that.
Yeah. So how do you keep the caches up to date?
Yeah, exactly.
Yeah, and they actually propose a few ideas for this. One idea is for the server to basically keep track of which caches are storing its page,
Okay.
and then just notify them whenever there's an update.
Oh.
They even suggest using something called multicast.
Multicast?
Yeah.
What is that?
So it's a way to basically broadcast these updates
Yep.
to all the relevant caches simultaneously.
So instead of each cache having to constantly check for updates,
Right.
the server just pushes the changes out.
Exactly.
Yeah.
Okay. It's much more efficient.
Yeah.
Yeah.
It reminds me of how social media platforms
Mhm.
send out those notifications, when
Yeah.
there's a new post or a live stream or something.
So a similar principle.
Yeah.
Yeah.
Okay, that's cool.
And even without this, fancy multicast technology,
Yeah.
the paper outlines a way for the caches to kind of communicate these updates down the tree.
Okay.
So only the caches that actually have copies of the page
Uh-huh.
receive the updates. It's all about minimizing unnecessary traffic
Yeah, that makes sense.
and keeping things streamlined.
Yeah, these researchers were really forward thinking.
They were, yeah.
They were already anticipating the need for dynamic content and real-time updates.
Yeah, they were ahead of their time.
Yeah, that's cool.
Yeah.
But let's shift gears for a second
Okay.
and talk about something else that they touched on.
Right.
Fault tolerance.
Okay.
What happens if a cache crashes
Right.
or a server goes offline?
Right.
Does the whole system just crumble?
Well, that's where the beauty of those random paths comes in.
Okay.
Remember how each web page gets its own random tree of caches?
Yeah.
Well, if one of those caches goes down,
Uh-huh.
the request can simply take a different path through the tree.
It's like having backup routes.
Yeah.
In case of,
Exactly.
road closures.
Yeah.
So the system is designed to be resilient
Right.
and adapt to these unexpected failures.
Exactly. Yeah.
But what if a whole bunch of caches go down at once?
Well, that's a great question.
Is there a limit to how much it can handle?
So the researchers actually tested their system against what they called an adversary.
An adversary?
Yeah.
Like a hacker?
Not necessarily a malicious hacker,
Sure.
but more like a worst-case scenario that they wanted to test against.
Gotcha.
And their system actually held up remarkably well.
Oh, wow.
Even with a significant number of caches going offline,
Uh-huh.
a good portion of the requests still got through.
So even in the face of disaster,
Yeah,
the internet can keep chugging along.
it can.
Yes,
Yeah.
that's reassuring.
It's pretty resilient.
Yeah.
Yeah.
But how do we even know if a cache is down?
Right. So detecting failures in real time, that's a
Okay.
whole other challenge.
Yeah.
This paper focuses more on the tolerance
Right.
than on the detection.
Okay.
Their goal was to create a system that could gracefully handle failures,
Mm-hmm.
regardless of how quickly we could identify them.
Right.
Yeah.
That makes sense.
Yeah.
And thanks to consistent hashing,
Right.
even if we do detect a failure,
Yeah.
reassigning the work to other caches is pretty easy.
Right. It's very efficient.
Yeah, it's like a self-healing system
Yeah.
that automatically reroutes the traffic around the roadblocks.
Exactly.
Genius.
Yeah, it's a cool system.
So we've talked about hotspots.
Yep.
We've talked about caching,
Yeah.
random trees, consistent hashing,
Right.
fault tolerance,
Dynamic
content. Even we've explored some potential applications beyond web caching and even some potential downsides.
Yeah, we've covered a lot of ground.
But there's still one big elephant in the room that we haven't really addressed.
Oh.
Time.
Okay.
We've been talking about this whole system of random trees and consistent hashing as if it all happens instantaneously.
Right.
But in the real world, things take time.
Oh, yeah, of course.
Like data has to travel across continents, signals have to bounce between satellites.
Yeah, the internet is not a perfectly synchronized clock.
Yeah, exactly.
Yeah.
So how did the researchers take into account these like unpredictable time lags?
Well, so that's a really important point.
Yeah.
The internet, as amazing as it is not a perfectly predictable environment.
Yeah.
There are always delays and hiccups and unexpected detours,
Right.
And as the paper points out, this makes modeling the internet incredibly complex.
Okay.
So the approach they took was to kind of simplify things a bit.
Okay.
They focused on the rate at which servers receive requests.
Okay.
It's not a perfect measure, but it gives you a handle on how much traffic a server can handle before things start to break down.
So instead of trying to predict the exact timing of every single request, we look at the overall flow.
Yeah, like measuring the current of a river rather than tracking every individual water molecule.
I like that, yeah.
Yeah.
Okay, so
And this actually ties back to the concept of cache size that you mentioned earlier.
Yeah.
So if a cache is too small, it's constantly having to evict old pages to make room for new ones, which reduces its effectiveness.
It's like trying to fit an entire library into a shoebox.
Exactly.
Yeah.
Not very practical.
Yeah, not very practical.
So bigger caches are better, right?
Yeah.
But obviously there's a limit on how much storage we can realistically have.
Right, of course, yeah. So there's this trade-off between cache size, the rate of incoming requests, and the load on each cache.
Exactly. Yeah.
And the researchers actually came up with some pretty fascinating formulas
to
kind of quantify these relationships.
Yeah.
And they highlighted the importance of finding the right balance.
Right. It's not just about throwing more hardware at the problem. Yeah.
It's about designing a system that's optimized for efficiency and resilience.
And it seems like consistent hashing plays a key role in achieving that balance.
Yeah, it really does.
Yeah.
It helps to distribute the load evenly.
Yeah.
To minimize disruptions.
Yeah.
And to ensure that the system can adapt to changing conditions.
So it's like having like an intelligent traffic management system that's keeping everything flowing smoothly.
Exactly.
Even during rush hour.
Even during rush hour, yeah.
This has been an incredible journey behind the scenes of the internet.
It has.
It's made me really appreciate all the complex mechanisms that make our online experience so seamless.
You know, we take it for granted a lot of the time.
We really do. Yeah. You know, we've seen how consistent hashing combined with those random trees really revolutionized web caching and tackled that dreaded hotspot problem.
But as we've discussed, the implications go far beyond just that.
Oh yeah.
You know, this research has sparked countless innovations.
Right.
And it continues to inspire new ways to manage and distribute information.
Absolutely.
In our increasingly interconnected world.
Yeah, it's really fundamental.
It is.
Yeah. It makes you appreciate all those times that a website loads effortlessly or you stream a video without a hitch.
Right.
You know, there's a lot happening behind the scenes.
There is,
to make that possible.
Yeah, it's really a testament to human ingenuity.
Absolutely.
And the power of collaboration.
Yeah.
You know, in solving these complex technical challenges.
It's really inspiring.
It is, yeah.
Yeah.
And remember, this research is from the late 90s.
Right.
The internet is constantly evolving.
Yeah. Who knows what's next?
Yeah.
What amazing innovations are just around the corner?
Exactly. So what do you think?
Yeah.
Could consistent hashing revolutionize other areas beyond the web?
Right.
Are there hidden downsides that we haven't even considered? Let us know. Until next time, keep exploring, keep questioning, and keep diving deeper into this fascinating digital world.